Coming up on the FTC Open Alliance Show, 19075 Clockworks from Romania is in the showcase their current progress that they're going through. They have a very interesting way of intaking and then shooting on the other side that we'll be diving a bit more into and some of their evolution that they've gone through on the robot. They're also doing a really cool custom planetary motor modification for goBILDA motors as well too that I think a lot of teams will be interested in seeing more about. They have that on a wiki too and open source for teams to dive more into, which is great. We'll wrap up talking more about some PID fine-tuning, kind of their progress they've gone through as they try to modify their flywheel shooter, get as perfect as possible. A lot of great stuff that teams can learn from. So let's learn more about their progress here on the FTC Open Alliance Show. This video on fun is brought to you by our viewers, supporters, members, and also in partnership with the following. For over 100 years, Kettering University has offered a better education because from day one, that education has been built on hands-on, co-op learning. Kettering's impressive alumni network includes founders, presidents, CEOs, and frontrunners who have a reputation for transforming industries with their resolute leadership. Apply today at kettering.edu/first. Take on the decode season with Studica Robotics, featuring their FTC starter bot, new 6mm hex shaft and motor options, and updated bevel gears. FTC teams can receive a 25% discount and apply for grants at studica.com/robots. Let's welcome on to the FTC Open Alliance Show, 19075 Clockworks coming in from Romania. There's a lot of great progress going on with this team, and I can't wait to dive in more to what they're doing. So welcome, everybody. Why don't you let us know who you are and what you do in the team before we hop right into your progress.
Hello, my name is Radu.
And I'm Alex, and we're from the mechanical team.
I'm David. And I'm ID. We are from the software team.
Okay, so this is our robot. It's been the whole progress started in the first 16 hours of the competition. At first, this whole magazine was fixed like this, and we couldn't take artifacts from the ground. The only way of taking balls, the only taking artifacts was from the human player and launching them with our flywheel. After that, after we won that competition, we decided to improve this design because we saw a consistency in the outtake, and we decided to make it pivotant like this with one Stingray gearbox right here with a servo and one here without the servo for stability. And also we added this rubber band intake that has an 1100 RPM motor connected to it. For the outtake, we have a pretty simple design with one servo that pushes the artifacts into the flywheel. The flywheel has one 84 RPM DC motor that has a custom gearbox which increases the RPM from 84 to 4200. We'll talk more about that later. And yeah, this is that's about it with our robots. I will try and do a demonstration on how it works. So here are the we'll wait for it to connect.
So while that's connecting, let me ask you in terms of robot-wise, some of the teams we've talked to decided to go a turret method. I love that your team is doing like an articulating height for it. Why was this method the best option for your team? And amongst your testing, is that something you think you'll still keep moving forward with?
Yeah, so we kept on this design. The other teams have that around the head outtake. We maintained this because it was consistent and it's a simple way to shoot the balls without the artifacts, without any special guiding for the ball. So it's we didn't want to complicate the design of the robot to maintain its simple aspect and idea, so that we could upgrade on the next robot with more innovations and stuff.
Yeah, and also the positioning of the flywheel up here eases the weight and the distribution of it, because if it was being placed underneath the ball, it wouldn't be that consistent.
Yeah, it makes sense to me. And then I love the simplicity that goes into it, and obviously, hopefully, very quick cycles too. Yeah, let's take a look at the demo and see how this all works for you.
Yep. Yeah, that's pretty much it.
One of the things I just want to mention too that I didn't know until I saw you actually shoot this. So you're actually intaking from one side and shooting on the other. I thought the whole thing was going to articulate up and shoot, and I really like your decision to shoot from the other side so you don't potentially have to turn as much. Is that something when you were designing this, was that kind of top of mind? Like, hey, we want to minimize how much we have to move and turn?
Yeah, it's pretty. You can have pretty quick cycles like this because you don't have to rotate the robot, and also we didn't have a need to put a servo to rotate this whole system. So yeah, it could make pretty quick cycles. That was the main idea for us.
Well, and I think from your launch angles too, I think that's another big thing, right? Is you're less likely to get blocked the way that you're shooting as well because you're launching at such a high angle that way. Was that something you all thought of too?
We actually didn't really talk about this, about the not being deviated by other robots. Is that the chassis it's pretty big and pretty solid with metal goBILDA parts, but the angle isn't really much of a strategic thing. But I guess we can take it that way, that you don't really get distracted by any other thing on the field.
Yeah, and we're also pretty constrained by the channels in the middle that connect the two sides.
All right. What else do you want to dive into on this machine so far?
Sorry?
What else do you want to talk about on your robot so far?
Well, I think this is pretty much a robot. It's a pretty simple robot, a pretty quick to do robot. And yeah, we will try and continue its development with some lift on the sides, with some sliders and that work on belts. And yeah, this is that's pretty much a robot. We're gonna use it for the meets pretty much, and yeah.
Sure. So do you want to pass it over to your software and programming team?
No, first we'll pass over to our goBILDA gearbox.
Sure.
Planetary.
Here we have our open source project on Planetary Gears modification from goBILDA motors. So there are two types of modification: the Planetary Star Killer and the Planetary Star Spinner. The Planetary Star Killer is made to make a one-to-one modification, one-to-one transmission to the motor and the gearbox and the axle. So here we have the motor. This is a printed part from printed with ABS. The center wheel, center gear, it's merged with the plastic around it. And into the motor, it spins at the exact rate of the motor electronic. The Planetary Star Spinner modifies the RPM of a motor from let's say that, like we presented you on the robot, from a 64 RPM motor to an 4200 one. So here we have the gearbox basically, if I make it spins, you can see because of my hand, but the center wheel is spinning at different angle speed than the axle, rotating it, and it just comes with the exterior of the motor, like the goBILDA, just the goBILDA exterior, and then the motor up here.
And you'll have a really good, I think, exploded view of this on your build blog as well too. I'm going to put up on screen, just kind of show how this all comes together as well. So a lot of great stuff going on. So just to kind of recap on, this choice to do this, was this more because like due to the sizing constraints, or like what really made you want to do some of this customization?
This whole customization was made because we lacked some RPM motors, and we decided that because we have a lot of 84 RPM robot motors and we don't really use all of them, we tried to make some way to make them in some way useful.
Sure.
And all of this customization, making them any RPM that goBILDA has, really eased off our progress, because we don't have to wait for ordering some other motors. We could just modify these ones.
Also, it being an open source project, it's very useful for other teams to who don't have like lots of money to spend on different motors, to just modify what they have into something they want.
And your team has a wiki page that others can access as well too, to get to your GitHub and other areas for this, right?
Yeah, our wiki page has it has the CAD, every part of the goBILDA motor, and also some custom parts that have to be either printed or cut from metal CNC. Are on our wiki, all the dimensions, everything you need, and it is explained to the last detail.
I love that you make that available for teams. That's really awesome for it. Anything else that you want to cover on this at all?
No, that's pretty much it.
All right, well, let's pass it over to your software team to talk more about some of your PID tuning in regards to your flywheel shooters. So let's jump more into it. I know we got some stuff to share on screen as well. So, guys, what do you want to talk about?
Well, first of all, we'll talk about the robot code. We have a functional tele-op mode, which has a pretty simple architecture of state machine design with an intake, shooting and idle position, and a launch chain that prepares the two servos that control the barrier and the flap that activates the shooting part of the robot.
We also want to talk to you about the PID of the robot that we use to control and to sustain the flywheel, the speed of the flywheel. So PID is a control system algorithm that we use for different sensors and for different inputs and outputs to keep the level steady and to not let it pass after a value, a predetermined value.
The current tests that we did were about the flywheel velocity, and we were looking to keep the speed constant and predictable in order to have an accurate shot.
Here we have more graphs. So we've covered the PID factors that we have to modify and to find empirically. We have the key KD, KA, and KP, the proportional, integral, and derivative constants. First one is the undercompensated KP. So this shows actually what happens when we have the little of a KP, and it doesn't.
It results in a very little reaction to the error, and the consequence is the following.
The curve that you can see here. You can compare them. So here down, you can see how it behaves when you have a more stable KP, and it grows more steadily and a bit more aggressively. It doesn't lag as much behind.
The spikes you can see here are from the shots performed by the outtake system. And we were looking for the recovery to be constant and predictable, which in this case is an example of a steady state error. As you can see, the levels between each shot are different, and this means we cannot we don't have an accurate depiction of the speed.
Yeah, so the error actually it sums up in time and it adds, so it grows more aggressively and you won't be able to stabilize it in time. First it undershoots, then it overshoots, and you can see clearly happening in the next graph.
So how much of a tolerance is there though for those shots? Because like, I mean, I know that they're not quite stable, but are they stable enough to still score, or when you're actually shooting, are you finding there's a huge variance?
To make everything easier for our driver team, we believe we should keep each shot constant and stable enough so that we know that every shot won't overshoot or
undershoot. Yeah. And also, if it overshoots and then it undershoots because of the integral or the derivative, it will start to oscillate, and the speed of the flywheel will start to also oscillate, to go down or go up. And this will affect the overall performance and will be really annoying to apply, especially when we'll apply it to our position, to the position of the robot, and we'll add the odometry. If we don't keep it steady enough and it starts to oscillate, the robot will go crazy. It will go left, right, and it will be really.
This is for the future auto.
Yeah, we'll develop it this week. So
looking for.
Yeah.
This is another example. In this case, the integral constant is not enough, and you can see here it takes time for the velocity to reach the desired level. In this case,
you can also see if we compare the graphs. So here we have the Ki constant equal to 25, and in this graph we have it equal to about 13. So yeah,
increased but not enough.
Yeah.
So what would you say your target recovery time is between shots? Like how many milliseconds do you want to get between you're ready to shoot for your next one?
We haven't exactly tested it, but the current code has a 400 millisecond delay between shots built in, so that the barrier has enough time to keep the artifacts in position.
And also the settling time after the shot is performed is quite satisfying. It doesn't take too much to settle on the wanted target, on the wanted level, so it's perfect for our drive team.
The last one of our graphs shows how exactly we desire the output of the flywheel to be.
Yeah, you can see it averages exactly on the desired power level. So it goes a bit up, then it goes down, but it doesn't go too much to oscillate and to create other problems.
We expect the fuzzing around the bar to be more of a hardware issue of the encoders inside the motor rather than a PID issue in this case.
So competition's coming up soon enough for you guys as well. What are kind of some like immediate next steps after this now? Like, is it just more fine tuning? Are there any other major things you're looking at doing? Walk me through some of the next steps.
Well, the next step, we're looking to start the auto.
Yeah, with Pedro.
Okay.
Also, we have to do more tests and probably some fine tuning on the parameters to find more. Perhaps we also have to consult the drive team and to see the controls to put them desirably. Yeah,
we need to collaborate in order to create an experience like this.
Yeah. But I think that this season the controls will be more easier for the drive team. They're quite forward, especially for our robots. We have used the state machines to make it easy for them to go between the shooting part and the intake part. And I think it's quite is good enough for them, and it helps them perform better.
Well, I just want to say, Clockworks, thank you so much for taking the time to come on and give us more about your progress for things. Of course, you can follow along on their build blog, so make sure you keep an eye out for that. But we can't wait to see your continued progress as you go through a lot of great things, and we know that your team's just going to keep improving and getting better and better. So thank you for taking the time, and best of luck as you enter competition season. Thanks a lot.
Thanks.
Thank you a lot.
Thanks for watching. Don't forget to like, subscribe, and click the bell to stay up to date on future fun videos. Take on the Decode season with Studica Robotics, featuring their FTC starter bot, new 6mm hex shaft and motor options, and updated bevel gears. FTC teams can receive a 25% discount and apply for grants at studica.com/robots. For over 100 years, Kettering University has offered a better education because from day one, that education has been built on hands-on, co-op learning. Kettering's impressive alumni network includes founders, presidents, CEOs, and frontrunners who have a reputation for transforming industries with their resolute leadership. Apply today at kettering.edu/first.